Video 36 of the Foundations of the Computational Economics course is a practical video where we will code up the simulator for the stochastic consumption savings model that we worked on in the previous video, and we'll look more generally on simulating data from economic models. So as you remember, in 2 videos ago, in video 33, we were looking at how to create random draws, according to a given distribution, and we looked at various modules in Python that allow us to generate this random variables. And we also learned about the inverse transform sampling, which is a versatile technique to generate random variables from various distribution. Now here we are extending this framework and sort of taking it to use with economic models. And we will have the situation where there's some model, the structure of the economic model denoted M here, and it has inside of it, some random components, I denoted epsilons here, with known distributions. And the whole model is becoming a function of these random components, and we're interested in the random variable created by this combination of the model and the epsilons, which are referred to as shocks often. Even though the distributions of the epsilons may be clear and easy, there can be many of these epsilons in the model, and they may be interacting in some particular ways that complicates the distribution of the random variable of interest, x, and makes it hard for us to sort of find an analytical distribution of x, which we are interested in, and then we can use this tool of simulating draws from the model, referred to as simulating data from the model often. So here's an example, and we've done that in video 20 already when we looked at Markov chains. We can think of a Markov chain being an economic model, a structural model, where the structure is given by the transition probability matrix P. And then the shocks can be thought of as the uniform random variables on 0, 1, so standard uniform random variables that we actually did use in the code to generate transitions, or to simulate transitions inside of the Markov chain. So for a given initial state x naught, just thinking about one trajectory of the Markov chain, we can use the appropriate row of the matrix, of the transition probability matrix, to simulate x1, and then, given the current state xi, we can do the same thing to generate xi plus 1, and do that, loop through this process for a given number of steps. And that would be a trajectory generated from the model, a simple model that is just an unconditional transitions given by a Markov chain. But that would be already an example of generating data from a simple economics model. Now let's look at a slightly more interesting example, which is a coin flipping game. So imagine that you're involved into a game where the coin is flipped sequentially, and probably it's a fair coin. That's going to be a parameter that we can change. And then if 3 heads come up, then you have to pay $10. If 3 tails come up, you will receive $10 as a benefit. Now, this is not too complicated, and I'm sure many of you can write the distribution of wins after a number of coin flips, 100 coin flips. Maybe a slightly more involved problem is the expected number of tosses to, say, win or lose $100. But we can approach this problem in the same way. We can write down an economic model, code it up, and then just simulate data from it, and then study the data. And this is what we're going to do here to start with, before going into the actual, real-life coding of the simulator for the consumption savings problem. So here's a little function called game, and that's a coin tossing game. The probability of a particular heads or tails come up is going to be 0.5 for the fair coin. The number of steps, so the number of flips, is the argument to the function, default 10. Stopping is another argument, and let me come back to that. It's not given by default. And okay, we can make some outputs that are switches, that can be turned on and off. Let's first initialize a bunch of variables here. So I is going to be just the counter for the flips, for the tosses. Tails and heads are the indicators for the state of our game. So whether there were 3 tails or heads, or how many tails or heads had been in a sequence so far before the next toss. And the balance is just the balance of wins and losses. And I want to store this balances as we toss the coin, so it's going to be a list. We will have a loop, and we will exit from the loop using break. And so the loop is just going to run indefinitely here and while true. Here's the coin toss. So how is that done? The NP random returns a single draw from the standard uniform distribution. So it returns a number between 0 and 1. And we just compare it to P, which is the probability of, say, a tail. Or I guess it's a probability of the head. So if the number that generated between 0 and 1 is above that probability, that means that the event occurred, which is the opposite, right? The complement probability, 1 minus P. So essentially what's going on here is we have a unit with P somewhere here, a unit interval, and it's like we're dropping points into this unit. It's almost like a Monte Carlo that we use to calculate pi. So the random is basically dropping a point, and then we are comparing it to P to see whether it fell into the first or the second half of this interval. And if it is in the first half, then we say, if it's in the second half, then we say tail. And if it's in the first half, we say heads. All right, so that's our generator for the shock, which is the small epsilon that we will combine. We will combine many of them into the an interesting event, the event of interest in this model. Okay, what happens then? Then we just print out what came up on the coin, and then this block is going to be important. Here we are incrementing tails by 1 if it is a tail, and reset the counter of tails to 0 if it's not a tail. So this essentially counts the consecutive tails or heads, right? Because if it's not a tail, then it's the counter. This counter drops down to 0, and the same thing with heads. It goes up by 1 if it's not coin, and coin is a Boolean variable here, right? So if it's heads, and otherwise it drops down to 0. Okay, then we increment the counter for the number of tosses, and if this counter gets above the n steps, the number of steps, then we say done after so many steps, and we break out of the loop and return, the ending, the final balance, and the balance history, and the number of tosses. That's what the counter is for. Otherwise, we check the conditions, right? So if there were 3 tails or 3 heads, then we either increment or decrement the balance. And this is the line that defines that increment. And then the balance gets appended, so we add a new element to the list, which is just the last value of that list plus the increment. And then we also reset the counts for tails and heads. So if we have say heads 4 times, and more, and or more, we're gonna count this 3 as an event, but not this 3, right? And the second 3 could be actually counted as an event as well, because this counter of heads would just be 4, right? It would just go up to 4. Maybe it's not. Oh yeah, and then it gets out of hand, right? Then it just increases, and we never get the new event again. But we do want to get another event if there are more heads here. If there are another 2. Okay, these are the details that could be defined in a different way. It wouldn't make much difference for the purpose of this simulator. It's just the rules of the game. Okay, and then we just print the change in the balance, right? The accumulating balance. Now, if this event didn't occur, even then we append the balance, which is just didn't change. So we just add the last element of the balance list once again. So the balance will hold the whole history of changes for all flip of the coin. All right, and then, so I've talked about this already, and then if the stopping rule is defined, and the stopping rule is going to be a 2-element array or a list, and we will check whether we are at the boundary below or above that are given in the stopping rule. And so here we can check whether the balance is going outside of the prescribed range of values, and if that's the case, then we also break with a message. Okay, let's run this code and let's see what we get. So if I just run with verbose with the default parameters except for verbose, that's what we get. We have a simulation, heads, tails. Oh, $10 we won. And then heads, we lost $10 down to 0. And then the last one, and we stopped after 10 steps. And this is, of course, because the end steps defaults to 10. But say we can run a longer simulation, and the balance is what, minus 20 after 50, or minus 50 after 150. We're not lucky here. Minus 20, and I'm running it again and again by pressing Shift Enter, right? And the random number generator is generating new numbers, so these are new coin tosses. And here we have the whole history. And look, we won $40. Okay, so the next or another way to stop this game is to give it a stopping rule and remove the end steps condition. And the stopping rule is going to stop the game once we reach the boundaries, right? So the game is going to go for, 168 coin flips it took to reach the upper boundary of 50. Over here, if we are, setting the maximum loss at 30, here it took 332, and we can just simulate from this game just like that, right? So here's in 61 flips, we got down to the negative boundary and got a little bit unlucky. And so in this 310 coin flips, we got up to 100. So you can see that this the simulation now works as a generator for the random variables, essentially, for the draws from some distribution that we can now study numerically. And how do we do that? Well, let's collect some data. The data, this is a list comprehension, right? So it will run for I between 0 and 10. So this is just 10 runs of our game with 250 steps. The data will have, a list of outputs from this function, and each output is a tuple. So then we can just loop through the data, but we need to initialize 3 variables because each element of the data is a tuple, right? So the tuple will be equalized to the balance trajectory in rounds, and then we're only interested in trajectory in here. We can plot these trajectories, 10 trajectories of this game. Here we have balance on the vertical axis and the coin flips on the horizontal. Of course, quite elementary, you can get more data, and you may start getting the idea of where it's going. What's the distribution if we sort of look at it after so many coin flips? Well, here's another code here, and let's start it at... we're collecting the same data, and now we are running the game for 100 steps. We are collecting balances as a separate list. Here's the list comprehension that goes through the data, and we're only taking the first element in each tuple of this outputs from the game, and drawing a histogram. So here's a histogram of wins and losses after 100 steps. Does it make sense to you? What if we increase the number of rounds? Does it look more like something? And yet again. And if I run it several times, well, we get a peak somewhere. And sometimes it gets deformed a little bit. But it should resemble a normal distribution, of course. Okay, now what about the number of steps to reach the bounds? If I run this code and the bounds are set here for between 100 and 200, and the game is run 1,000 times to collect the data, and then we just collect the number of rounds that the game took to reach the stopping point, and then draw the histogram of this number. So this is the distribution of number of steps to hit one of the bounds in the flipping game, and you can see this as some sort of exponential distribution, I suppose. So this is the example of how we can assimilate data from a particular model, and in this case this is a simple model that works as a random number, random draws generation according to the structure of the model itself. And let's go back now to the more general setting and think about how we generate data from the dynamic models like cake eating or consumption savings now. So thinking about the general form of the Bellman equation, remember we have the value of the state, the utility of state indecision here, and then the expectation of the next state value. Let's talk about the general dynamic model. So let's look at the general Bellman equation. What is this expectation taken over? That's the expectation over the stochastic transitions of the state space, conditional on state and decisions that are taken in the current period. So let's just denote the value for the next period state as some function of the current state, current choice, and these shocks, the random elements of the model. In the consumption savings example that we looked at in the previous video, the random element, as you remember, was the income, random income, that entered exactly into the next state expression. The next period wealth was subject to the realization of the random income, and the expectation was taken over the distribution of those random incomes. So with this substitution, I can just plug this g function into here, and this now is the Bellman equation and the Bellman operator, of which we need to find a fixed point, of course, to solve the model. With the solution, let me just temporarily denote the solution of the model as v star. This is the value function that is the fixed point of the Bellman operator, and then the policy function is the argmax of the right-hand side of the Bellman operator with v star plugged in there, and this defines the optimal policy function. The policy function is the prescription of the best action in each possible point in the state space. Okay, now we can go back to our framework of generating data from the model. And by the way, there's a typo here. This should be equal. Over here. So after the model is solved, then we can represent or write down this function that converts the shocks into what we are interested in this random simulation X. And so what is this random simulation? In a dynamic model, each X is going to be a trajectory of some quantity of interest over the given number of periods in the model. And then we also have to have an initial condition, so the initial value for this trajectory to start somewhere. And then the shocks will be a series of shocks also there will be shocks in each time period. And even so, each of these elements could be a vector in itself if we have multiple random elements in the model in each time period. Well, in the stochastic consumption savings model, that's just going to be the stochastic income. Well, let's see what happens next is now we can plug, instead of this x, we can plug the g function. So g function of the previous state. So if in the previous period the model was in the state xt minus 1, then we could apply the optimal policy to that state to get the decision in the previous period, and combine all of that with the new shocks to get the state of the model in period t. There's another typo here, and the typo is where's my lost expression? We don't actually need this. Yeah, here's the recursive expression that I had in mind. So you can see that axes are now generated. The axes are generated from xt minus 1s and the shocks. I still need a bracket in here. Yeah, it's good now. And given the initial condition and the number of periods, then we can end all of this epsilons. Now we can generate the trajectories of the state variable, or in fact any statistics or any functions of the state variables as well. So when working with dynamic models, then we have both the solution, which is the fixed point of the Bellman operator, and the corresponding policy function, the optimal policy, and simulations, which is a completely different thing, and it's important to keep them separate in your mind. Now, simulation is a sequence of realizations or realized points in the state space and their functions, actually, starting from some initial point under the optimal policy. And so this is the simulation, right? The confusion sometimes comes from comparing the optimal policy, so the optimal policy function and its properties, with the simulated consumption or consumption paths or their properties. All right, well, let's come back to that. So how do we simulate data from the stochastic consumption savings model? We can write a simulator similar to what we just looked at with the coin flipping game or simulating function. And so it should take as input arguments some initial points in the state space, in the initial values for wealth, and the number of periods. And then we can generate, a number of trajectories right away. And let's write the simulator as a vectorized function, so it can work with and generate multiple trajectories in the same time. It would be also nice to be able to fix the seed of the simulation, so that we can compare simulations when changing the parameters of the model, or technical parameters affecting the accuracy of the solution, or economic parameters as well. All right, and here's the algorithm, which is fairly simple. We need to solve the model first to find the policy function and the value function. Initialize the simulated paths, fix the seed, and so do all the preparations, and then just loop for t periods, computing the optimal consumption choices and simulating the random incomes. Random incomes are the random elements of the model, so these are the epsilons that we need to simulate, and then combining them entails to calculating the new realized values of the of wealth and the corresponding optimal consumptions for these values. Okay, so this is the copy of the code from the previous video. I'll actually go to the normal notebook mode now. This is the Deaton class. And so let's continue working on this Deaton class. I mentioned that we want to create the class which is sort of a nice complete piece of coding work. And so we will work on the simulator and make it part of this class as well. We will be building up this class in the next several videos, actually. So far, what do we have? Here's an example of the solution. You know, this is not what we saw before with the number of iterations it takes to converge. And so, you know, to make it a little bit easier for ourselves, let's reduce beta to make it converge fast. You know, these are the iteration indicators, so that it runs a little faster. Yeah, I guess that's enough of the precision. I mean, it does. The solution gets a little bit wiggly up here in this area, but we can leave with that for now. So let's think about what needs to be done. First, we have to solve the model according to the plan here, to the algorithm. And then if the simulator will eventually be a method in this class, it would be nice for this method to first check whether the model has been solved or not. And that's only possible if we actually save the solution inside of the object as well. So the first step that I thought that needs to be done is we should save the solution of the model inside of the object. Solution is produced here by solve VFI, and so we can just say self solution and, you know, make it equal to something. Here's the solution. But now let's keep it as you know, let's store it as a dictionary, which would be nice because now we can have labels. So I want to say that the value is going to be the V1 and policy is going to be C1, and this is going to be saved in the solution in the object class. Save the model solution to the object. Okay, that was simple enough. No, it wasn't. I need strings in here. Right, and now we can say M solution, and we get a bunch of numbers here, right? Well, the solutions is actually represented by these red lines. Okay, so what was the error there was that when we're defining the dictionary, the keys should be strings, not just variable names. Yeah. Okay, now let's modify the representation of the class here. And I just want to mention whether the model was solved or not. So we can add another line to the representation here. \n is a new line character, right? So we will get a new line in the representation. Model is solved. But you can see that I can insert not in here if I need to. Should I say the model? Okay, and then we need to add into the outputs the output that will go into that placeholder, and we want to say not if. How do we check if the model has been solved or not? Well, it will only have solution attribute if if the model has been solved. So I want to check whether there is an attribute. So self has attribute, and we call that attribute solution. Else we output nothing or empty string, and so the model is solved. No, I confused these. So nothing if it's solved, and not solved if it's not solved. Let's test this. Oh, and I need to print. Has no attribute, has error. I think I remembered about how to use this. Attributes. Oh, it needs an object and then the name. Okay. So it should be, it's just an inbuilt function in Python. It's not a method of our model object. So it's not self dot, it's just, we just need to give it. By the way, let me write this. Just to make sure that I save it into the notebook that will be available in the repo. Okay, does it run now? Yes, the model is not solved. But after we've solved it, the model is solved. Okay, so we saved the solution of the model into the object itself. Now make sure the next period budget can be computed with simulated income. Right, so the way that we will proceed with the simulator is to initialize the simulator, so assign some initial conditions, initial values of wealth, and then we will have to calculate the next period wealth conditional on the simulated income, right? But we have a special function to calculate the next period wealth, which is here, and it substitutes income with the quadrature points because we wanted to be able to take an integral when solving the model. So this now needs to be adjusted to allow for the simulated incomes as well. But before we actually start implementing these changes, let's start writing the simulator function. So the plan here is the following. Let's start writing the simulator as a separate function, but do it in the way that it can be inserted into the module, into the object, into the Deaton object once we're done. So what's the doc string here? Simulation of the model for given number of periods from given initial condition. And the way I'm going to write it is as if it is a method. So self is going to be referring to the model object itself. So then we can call it by saying let me actually move this cell just a second. So I moved the cell up above the call here, and we can start calling the simulator with the model M and whatever the additional arguments should be here. And the additional arguments should be the initial wealth. And let me just say 1 for now. And as you can see, this is a scalar, but we will have support for the lists and arrays in here. And T is, say, 10, for example. What else do we need to say? Plotting. Plot equals, well, true. Of course, we want the visualization. Okay, so if I run all of this, Simulator is not defined. Simulator. Okay. Right. First of all, let's check whether the model is solved. So it has attribute self solution. Otherwise, need to solve the model before simulating. And so the alternative would be to solve it, actually call the solver from the simulator. But I think it's a bit worse alternative. It's much better to sort of force the user, yourself, essentially, to be conscious of what you're doing. Solution may take a lot of time, especially if you want to increase the accuracy. And so solution should be done separately before the simulator. And simulator can have to be called multiple times. And therefore it should be separated from all the actions that may take a lot of time. Now we wanted to be able to fix the seed, so let's make the seed an input as well, so that the seed of the random number generator can be fixed from the outside by the user as well. So if seed is not equal none, we have np random seed fixed to this, to the given value. And now we all set up to start the generation. Okay, so let's first deal with initial wealth. Let's recast it as array. And just in case it had multiple dimensions, we want to flatten it. And the better numpy Ravel, I keep forgetting. Numpy Ravel is a method that flattens the array, returns a contiguous flatten array, and it is different from flatten in the sense that it never changes never relocates the data in the memory, so it's faster. There are side effects though, right? So if you flatten one array, the changes in shape will carry on to all of this, all of the other copies of this array, where a copy is not a real copy but just a reference. So anyway, but this is not going to be important for now. So this is now a flat array and p array of initial values, initial wealths. Let's just see how many people we will have, and this is going to be how many trajectories. This is number of trajectories to simulate. So if init wealth was an array, not just a scalar, then n will be the number of people, while trajectories is essentially decision makers, people that we want to simulate. Okay, are we ready? I think we're ready to do the main loop. So for t in range capital T, I'd like to do a capital T plus 1 actually, because the initial wealth is not simulated, right? So we're simulating for 10 periods, and the zeroth period is sort of like the initial one. Okay, so what do we have to do? If we already have everything generated up to period t, then we need to make this one step. So essentially what we have to do, let's just start with commenting. Find optimal consumption. Find or draw random income. Find next period wealth, and then loop to find optimal consumption again. Okay, so how do we store all of this data? And then we return, the simulated data. Let's think about how to store the simulated data. And I think a good way is to use dictionaries again. And we can initialize the dictionary with what we want to store in the simulation. Well, wealth probably. This is going to be this. Let's make it an array. And then consumption, another array. Now, how big they should be, let's just make them empty. We can make them empty arrays of a particular shape. And let me think about this shape. So what do I mean here? So we have n different trajectories, and we want to simulate them for 10 periods plus store the initial value. So here we are. I'm trying to create the n by t, or t plus 1, sort of a table. So each trajectory will be in a row. Okay, so that's what this is going to create. And now we've allocated all the space in the memory that we need to store the simulation. So nt plus 1, nt plus 1, yep. And then, okay, so now sim of consumption. Consumption is a long name to type. Let's make it C and M. Okay, how do we find the consumptions? Let's think about the initial period. So the wealth is already known. We should probably put the initial condition, initial wealth, into the simulation already. So M, and this is going to be all of the zeroth, the first column, and we can say init wealth. Okay. Let me just type initial wealth in the first column. Okay, and now the first column consumption, the consumption in the zeroth period, that can be found by looking at in the policy function, right? So I have to have a policy function to return the optimal consumption for this given amount of wealth. All right. So how do I know the policy function? It is stored in self.solution under the name policy. Where here? Under the name policy. So I have. Let me put it here. Self-solution policy. These are all the optimal consumptions computed for the corresponding points in the grid of state space of the grid of the wealth. But do we know whether this is going to be on the grid? No, we don't. So we need to interpolate, all right, as before. And I'm just going to grab this interpolation call from the Bellman equation, because we had to do exactly the same thing there. So this is going to be the interpolation function. It's going to be on self-grid, but now we're not interpolating the value function. We're interpolating the policy function. Interpolation function for policy. Interpolation. Okay, and now I can find the optimal consumption. It's just the interpolation at the points of the wealth, and these are the points in teeth column. And of course, I want to save it into the correct column. Teeth column is just like that. Okay, so this is optimal consumption in period t. Okay, now we need to draw random incomes in period t plus 1. Let me check how we've set it up. So I need my Bellman equation. So I need to draw this epsilons. I don't have the Bellman equation, but I always can look at the code as well. So this is where we stopped, right? So we don't have the incomes, but here the expectation is taken over the next period income when we're doing this. So this is the next period income that I need to draw here. And this is going to be coming from random log normal with the sigma parameter from self sigma, right? We had the income following the log normal distribution. If you go back to the previous video, that's where I discussed that, and you can also check that in the code by seeing that we are inverting the log norm CDF here. Okay, here's my log normal income with a sigma parameter that is given by sigma. A new parameter is 0 by default. Let's check that last statement. Is it 0 by default? Mean default is 0, yeah. Okay, sigma is here. Now size. How many random draws do we need? We need exactly n of them here on this step, right? And then we can say that the next period wealth can be calculated by calling the next period wealth method of the model itself. So we need m, which is the current period. Oh, I'm putting this into the new column, but the current period m is in seems m in this column, in column T, and consumption, we just generated it. So it's here. And now I need income, which should be somehow given to this next period wealth method, right? And this is exactly what the point here was. Make sure the next period budget can be computed with simulated incomes. That's the functionality that the object does not have yet. Okay, so this we need to come back to, but once this calculation is done, then we should be ready for the next period, right? Find next period wealth. That's what it is. And essentially now we're just looping back to t plus 1, and then it should be t now we should look at this newly created column when we are on the next iteration of the loop. Of course, it's important to stop at the right place. And where do we stop? I guess if t is less than t plus 1, then it's only then that the next period exists. Yes, otherwise we are out of bounds with this NumPy array, because it was initialized to t plus 1 here. So if small t is equal to t plus 1, then small t plus 1 doesn't exist anymore, and therefore we need this additional condition. I think this is it. So now we can just return the sim, which is the dictionary of all of the simulated data. Let's see if it works. Simulator. We're going to be returning the sims. Need to solve the model before simulating. Yeah. How about now? So the model is solved. As array missing one required positional argument A. Okay. This is the init wealth that we want to convert to the array. And let me run this. Unhashable type NumPy in the array. Yes, that's right. So the problem here is that I need to have the key, and then I need the column there operator, column sign. Now the NumPy random has no attribute log norm. Okay, I guess I mistyped it here too. Log norm came from SciPy stats. We need the random number, random draws from log normal, right? Random variable RVCs, location, scale, size. So this is what we need here. RVS. Location, scale. Oh, it's called scale. How did we do it in the object? So S is our sigma. Okay. So we need to give it a sigma, not the scale. Just like that. Okay. Now, here's what we had to come back to. The next period wealth has to be somehow given the simulated income. So let's go back to the object for the model, and let's add an additional argument, which is the simulated income, y. Okay, and now all this machinery with third dimension and saving quadrature points in a specific dimension is not needed for the simulator. So let me just make a condition here. If y is none, then this branch will work. Otherwise, return m1 plus y. And m1 is the first part of the next period budget, and then y, we will assume that it's the right dimension. So m, c, and y should be the same dimension for this to work. So let me just add the comment here to say that this is needed for simulated y's, simulated income. And as you can see, we've added functionality to this function, but we didn't change its behavior for the inputs that would be used by the solver. So the solver should not be broken by this additional feature. And this is a good practice when developing the code, of course, to keep it backwards compatible. And also, is it now that this next period well function or method is growing so complicated with it, special conditions here? Maybe we can try to separate it out into several methods, to keep it clean. Why do we want this special function at all for the next period wealth expression? Well, for the exact reason that, as the models get more complicated, this is something that is specific only to the model and to this particular model. And so it's always a good idea to keep this model-specific details separate from the solver, so that the solver can be reused or maybe generalized later to work with other models. And therefore, it makes sense to keep this budget equation in a separate routine. But now it's growing more and more complicated. Maybe it's becoming the time when we should somehow clean this up. I'm not going to do it now, but let's look at this one. We have a special case in the solution that the income has to be 0 if the number of quad points is 1. This should be actually the case for the simulator as well, right? So that we simulate from the model which we solved. So actually, we need to add this condition here as well. So that if the model has 1 quadrature point, then it's simulated and solved with the same budget, intertemporal budget equation. And this is the example where things get a bit too complicated for a simple thing like, r times m minus c plus y. Oh, okay, let's keep it this way for now. And let's see that things are working, and they are still not. Index 11 is out of bounds for axis 1 with size 11. Okay. This is in the simulator. We can see that the solver is working as expected. In the simulator, index 11 is out of bounds for axis 1 with size 11. Okay, so we went out of bounds when trying to save this. Oh, that's interesting. We're simulating for, let's simulate for 2 periods. Okay, it's the same thing. There are 2 time periods index 3 is out of bounds for axis 1 with size 3. Axis 1 is the second axis. So I just changed that. Okay, let me change it back. So t plus 1. We want to ensure that the next period exists. Okay, with the... does the t plus 1 exist? No. Okay, no, it doesn't. So it should be like this then, right? The first small t is 0, the last one is capital T, and we want to exclude the last one. The last one is capital T. So if t is less than capital T, then t plus 1 exists. Okay, that's the right one. Let me rerun that code, and now it's rerun. All right. So that's the simulator, and can we print the sims? Okay, so we have M array, M and C. Maybe print sims M without the dot, of course. So here's the simulated wealth, and the simulated only for 2 periods. Let's make it a little bit longer. Simulated wealth, and let's look at simulated consumption as well. And I want the separator to be the new line. Here's simulated wealth and simulated consumption. Do these numbers make sense? We start at 1 and we consume the whole 1 right in the beginning. Let's look at the optimal consumption rule here. So 1 is somewhere here, and we consume exactly 1 as prescribed by the consumption rule. Okay. And then we are left with this little... oh, no, we left with nothing. And then next period, we get some random income. And random income turns out to be 1.36. So it's a little bit higher here. And we are consuming 1.26 from it as prescribed by the rule here. And so there's a tiny amount left. And then the next period, there's new random income. We're going to 1.75. And so we are, again, consuming a little bit less than that. And then there is a little bit left. And the next period, random income is really small, right? And we are suddenly down here. And we're consuming everything again in this period. And everything again in this period. And everything is again in this period. So this is like a hand-to-mouth regime starting from this third period here. Okay, so this is the simulation. Let's also visualize it. Should we? And I think that's a good idea to have it right in the simulator code as well. So if plot, then I'm gonna copy a prepared already code just to make it quicker. And we need to change the alignment here. So n is already defined here. We'll have a couple of axes, title, variable, labels, setting up the axes. Okay, and here's the important part. So sim M and sim C is going to be plotted now with the row plotted together, right? So we're going through the rows with this alpha in the range of n, and we're plotting the whole row of consumption and savings. And we return sims from this function, of course. Okay, so these are the numbers, and these are the plots of these numbers. Let's make it a little bit more interesting by asking for init, initial wealth, init wealth, with a couple of starting values, say 1, 2, 3. Oh, and it doesn't work. Wonderful. It's always good to get some bugs right away and then be able to fix them. What's going on here? We go into simulator, the sim next period wealth sim. Okay. If y equals none, but y is not a scalar, right? That's why the truth value of the array with more than one element is ambiguous. Okay, so when we're checking for y equals none, while y is a vector, then this condition is ambiguous because we're checking element y's. And then we can just say if any of y's is nonce. That should fix it. All right, here we are. So 3 different people. They're starting from different initial wealths, and they're consuming a little bit differently as well. You can see that the range here, even though the lines look similar, the ranges are different. So consumption is always a fraction of wealth. And as you know, somebody's hit, this blue line is hit with the positive shocks of income, so wealth increases, then consumption increases quite a lot as well. And these are all the underlying numbers. I guess we don't want to see the numbers anymore now that we can have a nice graphic. Okay, going back to the difference between solution and simulation, this is very visible here. The solution of the model is plotted here. It's visualized with the value function and the policy function. Policy function is prescribing the optimal actions for different values of wealth. The simulated consumption, this is simulated consumption here, right? We've calculated the optimal consumption and the points of the state space which we simulated, and the simulation of the points of the wealth state space is here. You know, what's important not to confuse is the policy function with the simulated choices. As you can see, these are quite different things, and as we talk more about these models in the next videos, this distinction should be kept in mind all the time. Sometimes we're talking about the properties of the policy function, which is this function, and it, for example, has a kink at a particular level. Whereas the consumption functions may or may not have kinks, they're completely different things. Okay, we are done. We are done with the assimilator code. The last thing to do would be to take this whole method and this whole function and just implement it into the object. Now that we know that it works, implement it in the object. Redo the object, and now because we've written it with self from the beginning, where self just referred to the model that we gave in the first argument here, now we can instead say m.simulator, and everything should be working in the same way. So now our Deaton class now has a simulator method that allows simulation from the model, which is very nice and will be useful in the future. Let's run some larger simulations. We can use this notation here. What's the default value for plotting? It should be true. Yeah, that's okay. Solve is not the method of Deaton. Solve VFI, and that, of course, because we will add new solution methods later on to the same class. Init should be init wealth. Oh, and by the way, here I'm actually using log normal distribution to initialize the wealth. So people are, the initial condition is also randomized. That's absolutely possible. Here's a lot of people. Actually, let's let's start everybody at some large value of wealth. So this is 5 plus some shocks, or rather we could just make the shocks really large. So these are 15 people. Oh, it blows up, it seems. Say for 5 time periods. When sigma is really large, it's so easy to get the initial condition here, which is outside of the bounds of the solution that we've produced for this model. Remember, the upper bound is 10 on our solution, the wealth up to 10 that we can work with. Of course, we could actually increase that as well, m bar to 100, for example, and then I'm not completely sure what's going on here. All right. The initial wealth, one of them is really large. I think it's the initial wealth that makes this very strange, although. Yeah, interesting. So it doesn't make me think that the code at this time is working completely predictably and makes sense in all of the runs, but it's good. It's interesting. We will look at additional methods to solve the model and increase the accuracy. And actually, even here, we could just increase the number of grid points, and probably some of the artifacts that we just saw would be dealt with and would go away. But here we have a machinery in the end to solve and simulate a stochastic consumption savings model. And we're in good shape to look at alternative solution methods and more models in the next videos. Okay, I hope this has been useful, and I'll see you in the next video.